All right. Get the mic on again. You guys ready for the break? Yeah. Okay, so today I think we're pretty much done with the wastewater microbiology side of stuff. I guess what we're dealing with next is somewhat microbiology in nature. You'll notice that if we take a look at our syllabus, we're covering kind of the activated sludge with the recycle system last time, and so today we're going to get into BOD, effective oxygen demand in water. So we're shifting back a little bit. We're not going to really get to nutrient removal, recycle stuff. Maybe I'll mention it if we've got time at the end of that class period. But that seems all right to me, and I'm happy to give you some extra info on that for your, bedtime reading material to put you to sleep or whatever, if you're so inclined. So do let me know if that's something that's particularly interesting to you. So that's where we are. We've got really just 2 full lectures left, and then exam review, then the final. All right, so today, so we've already talked about this BOD stuff, right? We talked about microbe food as like, hey, this is what the microbes eat, and therefore they demand oxygen. Now we're going to really talk about, okay, well, how are we measuring that in practice, and what happens when we discharge that downstream into a river, right? So why we care about BOD in the first place. This is one of those conventional pollutants, right? This organic material. That's a large part of why we treat wastewater. It's because there's a bunch of dissolved stuff that microbes like to eat, and when they do, they're going to consume all the oxygen and it's going to go nasty. So all that rotting type stuff, fermenting, whatever might happen if you just let a pile of organic rich goo sit somewhere, we want to control that, confine that to our wastewater treatment, and so what we discharge, it doesn't have nearly as much of that. So BOD, we could call it biodegradable or biological oxygen demand. So it could be like biodegradable, biochemical, lots of terms like that. All basically saying biology is going to eat some stuff, and in the process consume O2, oxygen. So this is oxygen that is demanded in that sense by microbes breathing. Right? They're going to go through respiration, they're going to produce more cells, all of that. This is going to be their microbe food. So as we talked about before, it's going to be oxygen plus the substrate. We would call this dissolved organics the substrate S. And with that, they're going to use the organics partly as an energy source, partly as building blocks for new cell materials. And our outputs are primarily going to be CO2 and more cells. There's more than that, obviously, but the big picture is that's kind of the main components. We're essentially oxidizing a bunch of organic carbon. So there's a couple ways we could try to get an estimate for this amount that we will ultimately that bacteria will ultimately demand. BOD measurements is where we're going to go today. But before we get there, I want to just give a couple of examples of how else we might try to get to that answer, like how much oxygen is going to be consumed. That's kind of what we're after. So first of all, we could do a theoretical calculation. This is possible if we know exactly what organic material is there. So if we just had, for example, glucose, C6H12O6, and we said that's going to be our oxygen demanding substance when microbes eat it, we could then, in theory, set up a stoichiometry and say, okay, well, 1 mole of this plus some number of oxygen is going to be consumed and ultimately give us, well, if that's 6 carbons over there, we'll go ahead and say 6 CO2 plus some number of water, right? This would be the theoretical maximum amount of oxygen it could consume because all the carbon is being converted to CO2. That's kind of what we're after here. And anything else is going to water. So if we were to just do this quick little balance here, what we'll see, if we balance the protons here, we'll need 6 waters to account for the 12 hydrogens. And now we have 6 oxygens here, 12 here, so that's 18. We have 6 over here, so that leaves us with 12 needed, so we'll need 6 oxygens. So for example, if I've done that right, for every 1 mole of glucose, we need 6 moles of oxygen, right? So that would be the theoretical max. So this is just that stoichiometric kind of approach. And in practice, it's going to be very rare that we know exactly what kind of microbe food is there and exactly what quantities and all of that. And it's also pretty unlikely that we'll get exact complete conversion, right? So if we had sugar, some of it will build new cells instead of just be respiration, very likely. So that means not all of it will take oxygen. Some of it maybe just won't be completely oxidized. Maybe it'll take it to some intermediate, for example. So theoretical, it really is that the extreme case of we're not actually going to be there, but that would be the theoretical maximum, right? So then we also have chemical oxygen demand, and this is not describing anything different in terms of what we're measuring, but just how we're measuring it. So chemical oxygen demand would be taking a chemical approach to thoroughly oxidize our system. We'll probably heat it up, kind of burn it, introduce perhaps something more oxidizing than just oxygen, maybe blast it with UV, some sort of catalyst perhaps. We'll do something to give it highly oxidizing conditions and convert essentially all the organic matter to oxygen, plus oxygen, to CO2, water, nitrogen, and whatever else. Again, that's not going to be, we don't actually expect that to be 100% efficient to the theoretical, but it should get you fairly close. But that will overestimate the amount of oxygen demanded by biological activity. Because biological activity, we're just going to not be quite so efficient and aggressive with it. So we have 3 methods then. We have theoretical, we take the stoichiometry. We have the chemical oxygen demand. We send it through an instrument, blast it, and see how much oxygen comes out, or rather is consumed in that process. And then we have biological. And so 3 different ways to estimate. Theoretical is not really practical. Chemical is practical, but it's going to overestimate for us. Biological then is the last one. It's not as convenient as chemical, but it's much more representative of what we expect to happen in nature is what we're kind of caring about. So the deal is theoretical is going to be the highest estimate, followed by the chemical, followed by biological. And the reason we might want to use a chemical oxygen demand is because we can do that in a matter of an hour or something. You know, it's going to be a short time frame. Biological, we usually spend 5 days to let the microbes sit there and munch on the food. So as we'll see, when we define BOD, we'll often see it, and you probably may have noticed it in problems before. We'll usually write it as BOD with some sort of subscript. Typically that's 5. 5 is a bit arbitrary. It could be 3 days, could be 7 days, but 5 days is a reasonably convenient number. And if we do it that way, then we can just have a pretty consistent guarantee that the microbes have had enough time to do most of the eating that they're going to do. So BOD 5 is the convention. We have a couple subsets of BOD in general. We can consider carbon-based or carbonaceous BOD. We might call it CBOD. This is actually kind of what we normally think of when we say BOD, or perhaps that would be the simplest, most direct component of it. The majority of it for most wastewaters is going to be just from carbon, and that's kind of what we were just talking about. But there's also nitrogenous BOD, and that would be specifically converting ammonia, which is a pretty common byproduct of organic matter degradation. So you get a lot of ammonia in wastewater treatment, get a lot of ammonia if you have decaying plant material in the soil, for example, or things like that. So you'll end up with a fair amount of ammonia, and if you add oxygen, you'll get nitrite and nitrate. This is not balanced if you notice, but you could convert this to, it would normally convert to NO2 minus first, which is nitrite, and then you're going to need more oxygen to get it to NO3, which is nitrate. Eventually, you might be able to strip the oxygen off and get N2 gas, but that's a little more difficult. And of course, we balance this too. So, in order to take ammonia to nitrite and nitrate, it requires oxygen. This can also be a source of, like if we do this in reverse and we go into an anaerobic situation and we have nitrate, we can actually follow this backwards where microbes could take the oxygens from the nitrate and nitrite, use it as an oxygen source, as a kind of some energy there. And so if there's no oxygen around, they could actually make use of it in reverse. And so when they're going in this way, this is a little more typical. That's going to consume oxygen that we probably hoped would be staying in the water supply. Okay, so we could talk for a while about the nitrogen cycle in general. Ammonia is a pretty standard part of it, and we've got a lot of amine groups on organic matter that could, as it degrades, just come off as ammonia. All right, for the most part, we're not going to make or worry about distinctions like that. I just kind of wanted to let you know that there is a distinction there. We could calculate that. That might be a time where a theoretical calculation would be helpful for nitrogenous or something. If we were just looking at ammonia conversion, maybe that would be helpful. Okay, so how do we measure it? BOD 5, we're going to take a 5-day experiment. We're going to take some sort of a jar. It's pretty conventional to use about a 300 milliliter jar. It doesn't have to be that. It just seems to be a good working culture jar kind of size. We're not actually going to use a clear one because we don't want photosynthesis to happen, right? So we're going to either coat this in foil or something, or just use an amber jar that's going to block out the light that could induce photosynthesis, right? So that these amber jars would do just that. So we need to have it airtight because we don't want oxygen exchanging with the atmosphere during this process. We want to be able to count exactly how much oxygen was there, have it sealed, and measure 5 days later how much oxygen has been removed. That's kind of the goal. And this is dissolved oxygen, so we also want to make sure that we don't have any headspace there, so we can just check on what's in the water itself. So then we let it sit there for 5 days. We let the natural biological activity occur. However many microbes are going to grow, they're going to grow. They're going to munch on some stuff, and if there's a lot of stuff on there, they're going to pull out the oxygen pretty quick, right? And then you measure the dissolved oxygen after 5 days. So there's a bit of a caveat here. So we have a kind of a limit. O2 saturation is only 8 to 10 milligrams per liter. It's temperature dependent, but usually around room temperature, it'll be something like 8 to 10 milligrams per liter. There's a couple other things. Chloride concentration can affect it a little bit as well. But that's a good ballpark. If you had a very cold water, maybe you can get up to 16 to 18 milligrams per liter, but we're not interested in refrigerating our microbes, so we're gonna do room temperature. So that means we have to have some oxygen remaining when we actually do the measurement 5 days later. If you recall, our wastewater typically ranges between, I think we said 60 milligrams BOD per liter to, I don't know, something like 550, 600 milligrams BOD per liter. So that means that if we had even weak wastewater and we did a BOD test we're going to run completely out of oxygen before we can even finish the 5 days. And at that point, we can't really collect any data to figure out how much oxygen demanding stuff is there. We just know it's more than 8 to 10 milligrams per liter, whatever we started with, right? And so that gives us a problem, and it means we have to dilute. So then in the 60 milligrams per liter case, if we dilute by a factor of 10, then into just deionized water, just pure water, then we have 6 milligrams per liter. That we could measure, right? But if we had 600 or 550, we'd probably have to dilute by a factor of 100 before we could actually measure that accurately. So the wastewater strength then will tell us how much we have to dilute so that we can actually have the measurement in place. If we can't measure it because it's all gone, then we just don't know, right? So we have to dilute, and that's going to add in a couple small complications to our calculations. But overall, the calculation itself is pretty simple, right? On the face of it, if we have some dissolved oxygen initial minus some dissolved oxygen final, that's our BOD. Right? That's like the very simple term of it. Well, what's in the bottle at the start minus what's in the bottle at the end. Now, when we dilute, that'll complicate things a little bit. So if we started with some volume, we filled it just a little bit with wastewater, and then the rest of it we use some dilution water. I'll just say pure water for now. And then that bottle is filled. What we can say then is part of this has BOD, and we've diluted it, just do a very simple mass balance, and we can say, all right, well, our new equation is going to be the dissolved oxygen initial, DOI, minus DO final, divided by that dilution factor. So a moment ago I said if we had 60 milligrams per liter, but we diluted it by a factor of 10, that gives us, if we multiply that by 0.1, that gives us 6 milligrams per liter of BOD. So in this case, our dilution factor is 0.1. So let me explain that right here. So P will be our dilution factor. That's going to be equal to the volume of the wastewater in the total volume, which is the volume of the wastewater plus the dilution water. So it'd be total. And the total is often 300 milliliters. It's just pretty typical. So if we take an example for the P of 0.1, we could get there in 300 milliliters by saying volume of the wastewater is 30 milliliters and the total is 300. So that would mean in that case, the volume of the dilution would be 270. Right. Pretty straightforward. We do a lot of this anytime we're doing any sort of chemistry lab, so you probably have done this exact type of thing in the past. So it's relatively straightforward in that manner. The goal here, again, is to get our final oxygen in the actual bottle at a place where we can read it. Right? That's kind of the point. Okay, so let's take a look at this example. We have a 10 milliliter sample of sewage. So we already know that's our volume of wastewater. It's mixed with enough water to fill a 300 milliliter bottle. So we could, even just before we're saying anything else, V total 300 milliliters. So that should mean the dilution would be 290. The DO initial is 9 milligrams per liter. And then it says, to help assure an accurate test, it is desirable to have at least 2 milligrams per liter of a drop in the dissolved oxygen during the 5-day run. So we need for the oxygen to change at least a little bit, right? And they're saying 2 milligrams per liter is enough change for us to be confident about a change has happened and we can measure it accurately. So they want a 2 milligram per liter drop at least, and the final should be at least 2 milligrams per liter remaining. And really that's pretty common with the dissolved oxygen probes. If it's just a 0.1 milligram per liter drop, we're not sure if that's just noise. If there was just 0.1 remaining, maybe the sensor is just a little noisy and we're just not confident with it. So they're saying, let's give ourselves a 2 milligram per liter buffer so that we can measure between 2 remaining and a drop from 9 down to 7. Okay, so then the question says, for what range of BOD5 would this dilution produce the desired results? So we have some range of wastewater strength. You could say a minimum and a maximum wastewater strength. So take a couple of minutes and work on that. So we can take a look. If we take our equation, BOD is DO initial minus DO final divided by our dilution factor. We can solve for our dilution factor. That should be the volume of wastewater over the total. The volume of wastewater was given as a 10 milliliter sample. And the total volume of the bottle is 300 milliliters. So that's going to be 10 over 300 or 1 over 30. And I just went ahead and left it as a fraction because as we see, when we divide by that fraction, we can kind of just multiply by 30. Right, that turns out to be pretty convenient. So in this situation here, with the minimum amount of BOD that could get us in the readable range, we know that we have to drop that dissolved oxygen by 2. So we could just say from the get-go, the minimum drop that can occur is 2. If you wanted to, you could just call this DOI minus DO final as a drop. So the drop is 2 milligrams per liter, and you take that, multiply it by 30, and that gives you your answer, right? Is 60 milligrams per liter. In the other case, the drop should be 7 because we start with 9 and we're left with 2. So that means it'll be 7 times 30 is 210. Okay? Pretty straightforward, I think. Just maybe a matter of understanding what the question's asking for. Now, it turns out that we do have a bit of a complication. I would say this is more of an annoyance than a major difficulty or complexity, but it turns out that if we dilute water quite a bit, there tends not to be a lot of bacteria left if we're using pure water. And if there are, then they might be stressed and like not ready to grow yet. So it might take a few days before they like actually grow up to the point where you have enough bacteria to eat some food. So when we dilute wastewater heavily, we tend to have to also add in some bacteria. When we add in some bacteria, we tend to keep those bacteria in a solution that keeps them at least mostly happy to grow, somewhat able to sustain themselves, and we want them to be ready to grow as soon as we do this BOD test. So it turns out we have to have a little bit of BOD in the dilution water itself. So when we want to measure the BOD for our wastewater, we have to dilute it. But when we want to dilute it, we have to add in some more BOD. So it just complicates things a little bit. It's just a matter of dealing with the mass balance accordingly. So that's the next step, is to say, all right, well, in our seed water, we're seeding it with bacteria, that's going to add some BOD. So now we have 2 BODs to work with. And as we'll see in a minute, generally what we'll do is we'll have a bottle on the side with just the seed water, the dilution water, and say, okay, we'll let this happen for 5 days, we'll measure it, and we'll see how much oxygen is remaining in there, and then count that as like, all right, here's the BOD in the wastewater mixture, and here's the BOD in just the dilution water. Once we get those 2 pieces together, it's no problem. So we can measure this, and we measure this in order to calculate this. Since we can't observe the BOD in the wastewater directly, we get this dilution water, and we get our measurement of the mixture. So sorry for everyone online there. Okay, so then we have M as the mixture here, so we're going to measure the mixture. On the side, we're going to have a second bottle to measure the dilution. And one thing to note here, a P is obviously this dilution factor, but we can also rearrange P a little bit. We can say 1 minus P turns out to be VD divided by V of the mixture. So we'll use that in a moment to simplify and solve for BOD wastewater. Because it would be nice to have a formula that just says, all right, given these measurements, given this dilution, how much BOD is in the wastewater. And that's what we're going to here. So I just want to point out how we derive that. We can start with a mass balance to say that in our mixture, we have some BOD. And that's the volume of the mixture, right? That's in that 300 milliliter bottle, we've got some amount of BOD. And again, that's something we can measure. What we want to find, so let's just say that that is composed of two different things, right? The BOD of the wastewater in the amount of wastewater that we added. And it's also comprising in the BOD of the dilution water times the amount of dilution water we use. So it's just a very simple mass balance. We add two things together, and the final result is we have some mixture, right? That's all this is staying right here. So then we can solve for BOD of the wastewater. We're going to subtract this from both sides and then divide everything by volume of the wastewater. That isolates BOD of the wastewater. So to doing that, we get BOD of the mixture times the volume of the mixture divided by volume of wastewater. That minus BOD of the dilution water times the volume of the dilution water divided by the volume of the wastewater. Turns out we can ultimately get this as 1 over P, and we can get this as, if we extract things out, do a little bit of magic algebra stuff, we'll find that ultimately that becomes 1 minus P divided by P. That's not super intuitive, but we can do that recognizing that having a P on the denominator is just kind of handy. It turns it pretty close to what we had before, and the math does work out that way. So when we do that, we end up with an equation that says BOD of the mixture minus the BOD of the dilution times 1 minus P, all that divided by P. And that's our formula. Okay, so we just get that from a mass balance. Like I said, it's a little bit annoying perhaps, but now we have our unknown that we are after. This is what we want to know when we're monitoring our wastewater treatment to see how effective it is, right? This is the S that we might be looking for. This we can measure. That's our bottle number 1. And this we measure in bottle number 2. So after the 5 days, we have 2 measurements, and we can get what we need. Okay. Now, maybe we don't know how much to dilute it, so we might have to check a few different dilutions and have a few different pairs of these bottles to say, okay, well, actually, we only need the dilution water once, right? So we might have several different mixture amounts and go from there. Okay, so yeah, that's the point. One here would be just the full volume of just dilution water, and this one would be a mixture of V dilution plus V wastewater. So that might be a little bit of wastewater and then dilution. Okay, we can rewrite this same expression if we want to, using the actual dissolved oxygen values. Sometimes that might be handy, because what we had a moment ago was just saying BOD here, but our actual literal measurements are of the oxygen. So to put it in that term, we could say, in the mixture we have DO initial and DO final, and we're going to just use a different term to distinguish it, and we're just going to call it B. So B initial and B final for the dissolved oxygen in the dilution test. Or in the dilution water. Okay, so that's what's happening in this formula. It's otherwise exactly the same, right? That's just a way to say if we measured it, 9 and 2 in the one, 9 and 3 in the other, we just put all those together in their appropriate places. All right, does that make sense? All right. So let's take a look at another example and put that to practice. So we have a test model containing just seeded water, and it has its DO level dropped by 1 milligram per liter in a 5-day test. A 300 milliliter bottle, and this is separately, a 300 milliliter bottle is filled with 15 milliliters of wastewater, and the rest was seeded dilution water. And you can express that as a 1 to 20 dilution. And that experiences a drop of 7.2 milligrams per liter in the same period, the 5 days. So the question is, what would be the 5-day BOD for the wastewater? Okay, so take a couple minutes, solve that. All right, so hopefully you can kind of take a look and see it didn't actually give you exact values for the DO initial or final. So what you had to recognize is that it gave you a drop in DO, right? So that inherently tells you what is the initial minus the final. So it told us we had a 7.2 milligram per liter drop in the diluted case. That's our mixture. And remember, this is essentially the mixture case, whereas this is just the dilution. So we have 7.2 milligrams per liter drop minus the 1 milligram per liter drop. That one's going to be multiplied by 1 minus 1 over 20. This is going to be 0.95. 1 over 20 should be 0.05. All that divided by 1 over 20. And so we'll need maybe a calculator here, but we should be able to get that. Well, I mean, actually, we might not need a calculator. That should be 0.72 times, or minus 1 times 0.95. That should just be 0.95. Did you get the answer? Or the 6.2? Yeah. Or we could multiply 6.25 by 20, right? So let's do that. So 125 milligrams per liter. Okay, so there's our answer there. And I hope this also gives you some impression that, if we have raw wastewater, let's say in a bottle, it's going to cause a big problem for the dissolved oxygen, right? And it would do so even if it sat there open to the air for a while. Right? It's demanding so much oxygen that you could dilute it by a factor of 20, and it's still pulling out a lot of oxygen from that water. Right? So this is the reason for that BOD is a conventional wastewater pollutant. Right? It's like that's important. That's going to go kill a bunch of fish if we don't take care of that. Right? So fortunately, it's as simple as bubbling a bunch of air through the water, in some sense. Okay, so that's the majority of how we deal with actually measuring BOD. From here, I want to kind of shift gears a little bit to really think about what happens downstream. And the next lecture, actually, that's where we'll continue on with this further and get to actual sort of mathematical modeling. But I want to set the stage a little bit for the next 10-15 minutes on what that looks like practically speaking. So if we discharge wastewater, if you recall, our secondary treatment was supposed to remove about 95 to 98% of BOD. So that means we still have some BOD remaining. If we started with 500, maybe we still have 20 milligrams per liter of BOD. That's too much for if that wastewater was just all of the river, right, or all of the body of water, because that would deplete all the oxygen. So presumably, if we're discharging it, it has to be treated to the point where it's okay and it can be assimilated. It's not a bad thing necessarily for there to be a little extra organic material for biological life to consume. It could even stimulate some ecosystems in a sense. We just don't want the dissolved oxygen to be harmed or any other aspects of it. So if we think about what's going to happen to the BOD, if we discharge it right here at time 0 or at, that's where the discharge is for our wastewater, and then we track it downstream, we could look at it in terms of time or distance, especially if we're using a river or a stream. Of course, a lake or a pond, this is going to be a little different, act a little more like a CSTR scenario. Probably not ideal in reality, but something closer to that. So we're going to primarily focus on rivers and streams, but certainly similar calculations would occur for a lake or a pond. So if we track what happens to our BOD as we move downstream, generally what we'll see is we would have some initial dilution. And so after that dilution, at this point, it's going to be a little bit first order. So it'll probably, the more food the bacteria have, the faster they're going to be eating. And it'll probably decay something like that, right? The BOD will be consumed over time. Certainly there's other things that are adding it in, and there's probably some baseline amount just from the soil, rain, just natural processes having organic matter there. So there's almost always going to be some natural oxygen demanding substances there. But after we dose it with our wastewater discharge, from there it'll be falling off or decaying away a bit. Okay, if we take a look then at, let's see. I guess I meant to talk a little bit about oxygen here, but we'll come back to that. Another way to look at that would be total organic carbon. I would kind of do the same thing, right? That would be pretty much the same plot. As BOD, if that's an estimate we can use to know something about how much is there. And in fact, this is essentially, was very close to our COD measurement. So we can take a total organic carbon measurement and say, okay, well, how much organic carbon is there? That's pretty close to the same thing as identifying how much oxygen would be demanded if you oxidized all that carbon. So that would be kind of another tool we could use to estimate that. Now, the real thing that we're interested in is what happens to the oxygen as we go. So if we go down the river, we are consuming our organic material. We could mark some saturation level. If that's our DO saturation, then typically our normal river water will not be totally saturated, right? There's some natural oxygen demanding substances. So we expect, unless we just passed a waterfall or something, we expect that it's probably not going to quite be at saturation. So we might start just a little under it. A lot of times for our wastewater, we will, we've just spent a whole bunch of energy and process time to give it a bunch of oxygen, but typically then we have a clarifier and maybe a disinfection chamber. And by the time we're actually discharging, chances are the DO has also decreased again for a bit. So we would generally flush it with a bunch of air, get it up to near saturation point before discharging. So even with the wastewater entering here, it should be pretty close starting point for our dissolved oxygen to be up here. So we could then draw what happens to our dissolved oxygen as an increased demand starts pulling oxygen out of the system here. And it would probably look something like this and start heading back up towards saturation point. Now, this would be our actual dissolved oxygen that we measure. One thing to keep in mind here is sometimes it could be convenient to describe this as a deficit. And I'll explain why in a moment. So if we were to look at any point, well, let's look at the most significant point. If we look right here, that's essentially our maximum deficit. So oxygen deficit at its max. So we can look at how much oxygen is missing in relevance to how much should have been there, and that will be our oxygen deficit. So OD is important essentially because that's the gradient that drives oxygen to enter back into the water. So we'll say because it drives re-aeration. If we have water that would normally be saturated at 10 milligrams per liter, and it has 2 milligrams per liter, that that gradient there, that differential, is actually acts, like thermodynamically as a kind of a force to push oxygen back in the water. There's a lot that goes on there. We'll talk more about it, but things like how quick is the water moving? Is it turbulent? Things like that are going to affect what kind of a chance the water has to interact with oxygen and allow that reaeration process. So if you see all the nice looking fountains in the ponds in Louisiana, it's more than just looking nice. So I grew up in kind of North Georgia area, and there's some ponds around, but it's pretty rare to see a fountain in them, at least compared to down here. And a lot of that's because we really don't want the ponds to go anoxic and stinky, right? In order to support life and there's a lot of rich organic material here. All the sediment is kind of how our geography is here in Louisiana. And it tends to be very, very warm for a lot of the year. That's prime conditions to have dissolved oxygen deficits, right? And to make that nice looking pond not so nice to be around. But adding a fountain gives plenty of reaeration potential and keeps it a pretty nice habitat. And it looks cool. Okay, so there's a few questions then as we start approaching what happens to the BOD. I'm just going to introduce them briefly, and then we'll stop and pick up here next time. So BOD is going to be removed based on how much, based on how much BOD is remaining. So since microbes eating food, they're going to eat more when there's more food. They're going to eat less when there's less food. Okay, that's what we're saying here. So L is going to be a term we're going to describe as how much of that BOD is actually remaining at some given time. It gets a little confusing because we say BOD 5 all the time. It could be 1 day later, 2 miles downstream, and we say to ourselves, how much BOD 5 is still remaining here? So the time, when I say remaining at time t, it can get confusing there, but what we're really after is just to say, kind of like we're looking at deficit, we're looking at how much BOD is still there, so we can compare that to some amount of total BOD that if you gave it 10 years, how much oxygen was demanded. So it'll get a little confusing here, but ultimately that's going to give us a way to measure that BOD removal rate. Then we can, as you see, get some sort of a rate constant and take some sort of a mass balance approach on this L term, how much is remaining. Then we can add in rates, therefore how quickly are we deoxygenating, and balance that against how quickly are we reoxygenating or reaerating. So that's where we're going to be picking up next time. And with that, have a happy Thanksgiving and safe travels if you travel.